So I was asked to discuss neutrino phenomenology, and I think last week there were lectures by Andre. There are other lectures also where this topic have been introduced. This is a very interesting topic nowadays in particle physics, and I will see if I can convey something interesting to you guys. So let me start with a very pedagogical thing, and let me try to set the stage for our upcoming discussion. So when we stare towards neutrinos, one of the most important things that really makes me very happy, and it makes the feel enriched, that when you think about neutrinos, they are omnipresent, they are everywhere. And you can think of many natural sources for neutrinos. There are many artificial sources. And in the precision era, when we are trying to address harder problems, the importance of artificial sources have been increased by many folds, because you want to do your experiment in a very controlled environment. But in this nice plot, if you see in the x-axis, this is the energy, neutrino energy in the log 10 unit. And this is the distance that these neutrinos are traveling when they are reaching to you. Clear? So here, you see, when you see the x-axis, you have these 18 orders of magnitude in energy. I am not considering the even lower energy neutrinos like relic neutrinos from BBN or cosmic micro neutrino background, but I'm just considering the range where we have detected these guys, right? So you see, you have these 18 orders of magnitude in energy and 25 orders of magnitude in the base length. I'm taking time, so you can stare at the plot. So at very lower energies, the first thing that come into our mind is the geoneutrinos. These neutrinos are basically produced inside the Earth, in our planet, through the decay of heavy elements, like uranium, thorium. When they decay through beta decay, you get these in mostly electron antineutrinos, but they are very low in energy, but we have successfully detected them, right? They were first detected by Kamland experiment in Japan around 2005. And recently Borexino experiment in Italy. They have also successfully detected geoneutrinos, okay? So you see the energy range, like when you are at 10 to the power 6 eV, somewhere around, this is 1 MeV, right? Correct? So I am talking about neutrinos below 1 MeV. So for geoneutrinos, 2 experiments, Kamland and Borexino. And both experiments are over now. There are some data. If you are interested, you can analyze them. You can talk to those collaboration and they will be happy to give you the access. But those are over. Now there are experiments, like next year there will be one experiment called Juno in China. It's like a medium baseline reactor antineutrino experiment. They have prospects to see these geoneutrinos. They are capable. And also there are SNOW experiment. They can also see if there are some activity happening around. Then we have neutrinos, electron antineutrinos from reactors. So these are all in the MeV range. And then we have the sun, and sun shines in neutrinos. So I'm just giving you the landscape. Then if you move ahead in energy, then you have neutrinos from very short baseline experiments. So VSBL stands for very short baseline experiment. Okay? Now, what are the experiments we have? So in this category, we have experiments like SHOW, okay, Palo Verde, Double SHOW, Reno, Diabe. You can think of those experiments, reactor experiments. You must have heard about these names, right? Can you just raise your hands, like, when I say these name of the experiments, you have heard these names? Okay, good. Makes sense. Okay, good. So these are very short baseline experiments where the baseline is around kilometer-ish. Okay? And I will discuss that what was the importance of these very short baseline experiments when we uncovered the three flavor paradigm. But you know, one of the important experiment was Diabe, where theta 13 was discovered, right, in 2012. Then you have short baseline experiments. Here, mostly we are talking about the Fermilab short baseline program, where the distance is maybe 200, 300, 500 kilometer. And here you have this long baseline. You are familiar with Dune, which has a 1300 kilometer baseline. And in Japan, there is a T2 Hyper-K project, which has like 300 kilometer baseline. But look at the energy range that is covered by this long baseline, which is a subset of this atmospheric neutrino sector. So this is the typical energy range we probe with these two experiments. And in my lecture, I will try to focus on this band. Clear? My discussion, the neutrino phenomenology, will be covered around this band, where I will try to go back and forth between long baseline and atmospheric. But that doesn't mean that these experiments are not important. Lack of time. Okay, so in this area, in these energies, and you see here the path lengths that they covered. Like if these are placed there, that means this is the distance they traversed to reach to you, and these distances are small. And when we wrote testable today means we have been able to successfully detect these neutrinos from these various sources across this energy and path length. Now, if you go to higher energy, so by the way, when we detected neutrinos from sun and supernova successfully, we started the era of neutrino astronomy, which is a very hot topic in neutrino physics. I should be very precise, I should call it low energy neutrino astronomy. The moment we successfully detected neutrinos from sun and supernovae. Okay, so all of you know that 2002 Nobel Prize was given to Raymond Davis Jr. for detecting solar neutrinos and Koshiba-san from Japan for detecting supernova neutrinos. I don't have time, but there are many interesting stories. There are many interesting facts. If you want to go into details, how they discovered or detected these neutrinos. Very interesting. If you just pick up any neutrino textbook and start reading, you will get those stories and nice things. So these cosmic neutrinos, when we detected first time at lower energies, we started the era of low energy neutrino astronomy. But what is remarkable that over the last 2 decades, we have detected neutrinos from various sources. You see, when I say geoneutrinos, reactors, short baseline, atmospheric, solar, all these neutrino sources, if you think of how they work, how they produce neutrinos, what are the mechanisms happening inside in those objects, they are completely different, right? Just start thinking about sun. Okay, how neutrinos are produced inside sun, how neutrinos are produced inside supernovae, how neutrinos are produced in atmosphere or in our earth. The mechanisms are different. The energy spectra that we get is also different because they are at different energies. And the understanding that we have about these neutrino sources are also different, right? And they are traversing different distances. When we think about supernova, the distance can be, kiloparsec, megaparsec. But when we think about, solar neutrinos, then we have like 1 astronomical unit. When you think about reactor neutrinos, we have few kilometers of baseline. So the message that, because see, if you want to appreciate 3 flavor neutrino oscillation phenomenology, you need to appreciate that our data set is very rich. When we combine all the data to give you a very nice 3 flavor picture, all these neutrinos have contributed. But the unity in diversity, what I say, they are very diverse in energy and in baseline. Okay? Now if I move towards higher energy, Then we have a very successful experiment called ice cube. I will see, because as Srubabati mentioned that, we have been working for ice cube for last 2 years, and now more than 60-70% of our research time is going into ice cube. So we are fully, and my students are here, you can interact with them, what they are doing within ice cube. So ice cube was planned, other proposed, planned and executed to see or observe these high energy neutrinos, high energy cosmic neutrinos. We know they are there. We have some catalog, some sources which can produce these high energy neutrinos, but the exact mechanisms are unknown. So there are two open questions. We need to, once you start detecting these high energy cosmic neutrinos, moment you have the questions, do I know the sources? These sources are like point sources, or they are distributed, or they are diffuse, right? You need to know where from you have seen these neutrinos. When you see some activity in ice cube, and if you measure the energy of the neutrino, and if it is very high, and if it doesn't match with your background, you can tell, okay, I have seen a very high energy neutrino. But then the job is in hand. Do you know from which source it has come? First, if you know, now ice cube is in an era, they are also discovering the sources. Okay. Now, once you know, okay, I know from this source I have seen this event, then the question comes, what is the mechanism happening inside those sources so that they can produce such a huge amount of energy, right? These energies are way higher than you can think of producing in your lab. What is the highest energy that you can think of in particle experiments? CERN, right? 14 TeV, 20 TeV, they are talking about 50 TeV, 60 TeV. But you see the energy range that I'm talking about. So in 2013, when IceCube announced that they have seen more than 20 these high energy cosmic neutrinos, that was the time the era of high energy neutrino astronomy began. So how many years? That progress was very rapid. 2002, only 10 years. We had a big jump and we started the era of high energy neutrino astronomy. So you guys are very lucky. So you have chances doing great physics in lower energies, at higher energies, because many things are happening in low energy astronomy, in high energy astronomy. Clear? I'm taking time to set the stage. Now you see, if I go beyond TeV, PeV, you see this part, testable in next decade. We have not seen, again, there are theories, they postulate, they hypothesize that you should expect neutrinos in these energies, but if you study the fluxes, when you go in higher energies, fluxes drops, sometime with power law. So you see, when you go to higher energies, the amount of neutrinos you expect from these sources are dying, making your life difficult, and they are weakly interacting. But one thing, the neutrino cross-section increases with energy, so this is a good thing. But ultimately, to detect some handful number of events at higher and higher energies, when you move towards light, you need really bigger detectors. IceCube is 1 kilometer cube at the South Pole. You see the imagination, you went to South Pole, dig the ice, because you need a 1 kilometer cube volume. So you can just calculate how many events you expect in one day in IceCube. Just take some fluxes at those higher energies, and you have a typical neutrino-nucleon cross-section, multiply it and see with the number of nucleons available in 1 kilometer cube IceCube detector. Ice is like ice, water, whatever. You can calculate how many nucleons are there, right? All of you have a water bottle. So you can calculate, during the lunch, how many nucleons you have in 1 liter of water bottle. Just calculate it, small, okay? So then you can think of, you can immediately calculate how many nucleons you have in say 50 kiloton water detector, or like 500 kiloton water detector, or 1 kilometer cube ice, doesn't matter. Okay? So start from basics. So this is testable because even ice cube is not enough. That's why they are planning ice cube Gen 2, which will be 8 times bigger, like 8 kilometer cube. Okay? And they will put more photosensors, because the only way you can detect this vast landscape by making your detectors big and waiting for longer time, right? Because you are talking about some natural sources. You don't have any handle on them. Yeah, source bada do. Nobody will listen. Okay? But you can make your detector big, and you have to have patience. Okay? So this is the era which we are planning to test in the coming decade. And very exciting. That's why, I am also thinking to switch my gear from this era to little bit to this era, because this will be happening soon. With Ice Cube Gen 2 is one of the candidates. But China is even thinking bigger to have an experiment called Trident, which is even bigger. There is another experiment called P1. So, I just told you that I will give you some paths. You can start thinking, and maybe in future, some of you will work for these experiments. Okay, world has become short. If you have a vision, you can go there and work. Okay, so you have this huge landscape. So these are called ultra high energy neutrinos, and we hope that we will be testing them in the coming decade. Clear? So what is the take home message? To me, take home message was, we have overcome the bottleneck of neutrino detection. When it was postulated, Pauli mentioned that I have done a terrible crime. It will not be ever detected. So to me, the triumph in neutrino physics over the last 3-4 decades, forget about oscillation, fitting and all this, to detect these guys, that was the biggest challenge, and we have overcome that. That gave me peace, that okay, I can take my mind anywhere and think about all this crazy physics because I have the tools to detect them. That is the take home message. Second, we have detected these guys from various sources, and they span neutrinos over a wide range of energies and the path length. I am repeating over L and E because they are very important for my oscillation phenomenology. Okay? So we have the era of low energy neutrino astronomy, high energy neutrino astronomy. Perfect. Move. Okay. So when I think about neutrino oscillation phenomenology, in this big landscape, I'm just marking these 4 blocks: reactor, solar, long baseline, and atmospheric. So when we learned how to detect these neutrinos from these various sources, as you know, we landed up with some surprises, because every source, you have some theory, you sit down and you can estimate, okay, at a given point of time, at a given place, how many neutrinos I can expect from sun. This is called standard solar model by John Bacall. Okay, he gave us a precise calculation that how many neutrinos you expect from sun. Similarly, Honda-san did the calculation to tell us how many atmospheric neutrinos, if you plan a detector here in Bangalore, how many neutrinos you expect from your atmosphere from various directions. So we have a very nice knowledge how many neutrinos you expect from these various sources. By the way, I want to emphasize that now we are in the era, first our challenge was to detect neutrinos from these sources. We successfully did that. Then we discovered neutrino oscillation, because you knew how many neutrinos you expect from various sources. When you detected them efficiently, you didn't find the numbers. So there was something funny going on. And as Andre must have explained to you, the answer was that there is a quantum mechanical phenomena is happening called neutrino oscillation. Very like a Young's double slit experiment, an interference phenomena. But we observed that same trend across many sources, not one data set. We saw that phenomena in reactor antineutrinos, solar neutrinos, in long baseline neutrinos, in atmospheric neutrinos, even in very short baseline experiments. So the topic that we are going to discuss is very rich. It is not just one data set or some small number of events. You have a huge data set from various sources. See, so I'm just trying to encourage you that you think about the complexity when we say, oh, okay, this is a 3-flavor neutrino oscillation, but how the things are very complex when you think about, okay, I have information from 10 different things and I need to fit those information in one framework. So there is a huge chance that there can be so many errors. There are so many unknowns, right? So just in these lectures, you try to appreciate that how much our colleagues have achieved in this field. And once you get motivated, then you are bang on, basically. I don't need to tell you, ye karo, wo karo, khud karo. Okay. So mostly during my lectures, I will try to focus these two long baseline and atmospheric, but when I talk about 3-flavor neutrino oscillation framework, the contribution from these two blocks are also very, very important. But I want to mention now the research has come to such a stage. First, the issue was, let's detect those neutrinos. During detection, we had a funny surprise. Some of them were lost. Now we have an explanation, oh, neutrinos are oscillating. And that model comes with 6 different parameters, right, that I will talk about. We know some of them very precisely. But now the physics has moved to the question that, okay, can I infer about the neutrino source from the data that I have? Initially, you relied on your theory. Please try to connect with me. If you have a question, ask me. Initially, when you estimated how many solar neutrino events I expect, you relied on John Bacall. Okay, he has given the calculation and you estimate this many events. Now we have so much of data and they're so precise. And in between oscillations were happening and we know the oscillation framework also at the GeoEarth level. So you are asking the question, can I infer about the source itself from the data? That is one of the triumphs of precision era. Everywhere, in solar neutrino experiment, in atmospheric neutrino experiment, in other long baseline, every experiment, things are becoming precise so that you can ask the back questions. Like when you detect tau neutrinos, because first 2 generations are easy, right? Why? When you think about neutrino sources, can you tell me someone what are the basic processes we can think of to get neutrinos? Anybody? Be loud. Beta decay, right? Pion decay. So when I said we know the sources very well, like the spectra, because these are well computed at cross-section process, right? Beta decay is very well computed, well known. Pion decay is very well known, with some uncertainties, forget about that. Okay? So you know what is the neutrino spectra from a pion decay. By the way, what is the difference between pion decay and beta decay? Very quick, the major difference. Excellent, we are on the same page. So when you can estimate the 3-body decay of beta decay, you know what are the neutrinos with what spectra it is coming. And then if you have a boost, then you do the boost basically. Go to the lab frame, include the gamma. So you know the spectra very well. So you relied on some theory, but now when you go to number of events, which is the product of what? Flux, time cross-section, time how many nucleons you have in your detector, and some detection efficiency. You agree with me? Now, if each piece is very under your control, if you know the cross-section very well, you know the probability very well, you know the your detector very well, then you can move back and you can estimate the flux, right? Make sense? So it's very simple because, if you appreciate now this thing, then it will be easy for me in future classes. So when you say now number of neutrino events, we have 4 basic pieces. We have the flux of neutrino. I am not writing any flavor. Okay, now successfully we have detected E flavor, mu flavor, even tau flavor. So Let's don't talk about flavor. We have the flux, correct? Think about you want to plan a neutrino experiment. So first, ki flux kya hai? What is the flux that we expect from that source? That is the first question. Then you have what? Flux is coming to you, so you can take the 1 by 4 pi L square corrections, because neutrino flux is just like torchlight, right? When it comes to you, it will be divided by 1 by 4 pi L square, right? Number of neutrinos at the source and at the detector will be divided by 4 pi L square, because they are just spreading out, correct? So you know the neutrino flux at the detector level, suppose. You know the neutrino source, or you need to know the neutrino flux at the place where you have the detector. Then you have the cross section, sigma neutrino n, this piece, right? Neutrinos are neutral, so you don't see neutrinos directly, correct? So you need to see their charge cousin. So you need to know this cross section very well. You had 2 lectures by Sajjad, right? And he explained to you where we are now as far as these cross section measurements are concerned. And then this is neutrino nucleon cross section. Now suppose you want to plan a small detector with 1 liter of bottle of water. In super Kamiokande you have 50 kiloton of water. ठीक है, चलो मेरे पास 1 liter ही है, कुछ तो पकड़ेंगे. So here is number of, say, nucleons. That also we can calculate precisely. This is per nucleon cross section, and this is the cross section for the total number of nucleons. You wanna wait? So, chalo, include the time also. Let's wait for 10 years, 12 years, 20 years. And at the end, you can also think about the detection efficiency. Correct? This is a very crude picture when you want to estimate. I want to estimate this many events I expect if I do this experiment. Believe me, in the last 20 years, I'm doing the same thing every day. Okay? When I think about neutrino phenomenology. So now, in your experiment, you know this number. Adam is teaching you how to deal with these numbers. You have some numbers with some error, right? So he mentioned today you have X number of events with an error of epsilon. How to deal with the number of events, he is teaching you today, right? So this part you know, the left-hand side, correct? Suppose if you know this part, you know this, you know this, you know this. You invert it, you know this, correct? Idea is clear? So now we are, and okay, I forgot the most important part, the oscillation. If they are oscillating, it should come here, but okay, fine. It's a product, so fine. But now it has 6 parameters I will talk about. So we know the 0th picture of this also. Now if you are careful and smart, you can just divide this and you get this information about the flux. So I'm just telling you the present status. In all these sectors, now we are in that stage. We are asking about the properties of sources. Clear? I want to stop and I want to ask you, clear, this idea is clear? If not, ask me. Great. So when we started detecting this left-hand side from all these experiments, carefully taking into account all these pieces, we found that this part is not 1. Correct? So they were lost. Because you planned your experiment, okay, I can detect electrons very well, muons very well, or tau very well. So then, since they are oscillating among each other, you don't see all the flavors. And that was the triumph of Snow experiment, right? Snow neutral current experiment. They could detect all the flavors and they could solve the solar neutrino anomaly. That, okay, initially you had nu E, they must have oscillated to nu mu, nu tau, but now I see, because I can detect all the flavors and it sums up to 1. So you need that kind of measurement if you wanna establish that oscillation is the phenomena within your detector, within your experiment. you should be sensitive to all the flavors. Now, you will see, even till last decade, we were mostly relying on electron and muon flavor. All these experiments were planned to detect either electron, muon, or both. But in this decade, most of the experiments are also thinking, can we detect in some way the tau flavor also? Because in atmospheric neutrino experiment, nu mu, half of the nu mu is oscillating to nu tau, right? And you don't detect them. You are just ignorant about that part. But now the technology has improved. Our machine learning with AI, artificial intelligence, we are in that stage that we can also infer about tau flavor. So that is one of the happening areas in neutrino oscillation phenomenology. Think about, okay, they have fitted the data with electron muon. What if they could have seen some tau? Can I improve the contour? Can I improve the measurement? Think about it. In any experiment, okay, think about Dune, think about T2 hyper, all these future experiments. What would happen to my analysis if I can also detect tau? Okay, like the paper you wrote today for ESS and USB. Can they see some tau neutrino events? Okay, will they change your constraints? Correct? Think about it. So, when we detected these neutrinos, they oscillate. An oscillation demands that neutrinos are massive and they should mix. So here comes the neutrino oscillation, and you know the consequence, because neutrinos are massless in the basic standard model picture, right? Because experimentally we have seen all the neutrinos are left-handed and all the antineutrinos are right-handed. And to write a Dirac mass term, you need both left-handed and right-handed guys, right? So in the basic picture, like you can ask me, why can't we invoke right-handed neutrinos? Yes, you can. But in the basic picture, experimental fact is that neutrinos are, like theoretically, we don't have, ways to write neutrino mass term, because experimentally we have seen that neutrinos are left-handed and antineutrinos are only right-handed. But neutrino oscillation demands that they should have mass, so there is a clear departure. So before I begin and go in deeper, we should all appreciate that if you think about all the particle physics experiment, I'm not talking about dark matter, dark energies and all. Just think about all particle physics experiment. This is the only signature of physics beyond the standard model. Neutrino mass and mixing. Dark matter, dark energy, these are cosmic observations, I'm not. So think about all the categories of particle physics experiments. Okay, collider, accelerator, whatever flavor, neutrino oscillation is the exclusive evidence for physics beyond the standard model, because you need to expand standard model to invoke or to incorporate these 6 oscillation parameters, and also there are UKAO parameters, coupling also. So for that, Nobel Prize was given. So these 2 slides I incorporated to give you a big picture and to set the stage. Correct? Should I proceed? Okay, little bit of new physics. So I just told you that neutrino mass is in our hand now. We need to invoke neutrino mass and mixing in our picture, right? That is the job. That is the holy grail. And if you ask me, okay, what is the connection? You are talking about neutrino oscillation phenomenology. I know that I need to extend my standard model. How will I reach to that goal? How should I know that this is the right expanded new standard model of particle physics? But I can tell you, after 3 lectures, if I convince you that this is one of the ways to know what is the right key to open your door is to precisely measure this mass mixing parameter. You have thousands of theories, right? Every day you see in archive proposing that, okay, I have a way to incorporate this neutrino mass and mixing. Now all these models have allowed values of this mass mixing parameter. My model allows or doesn't allow θ13 to be non-zero. So the moment I discover θ13 is non-zero, my model is ruled out, right, at the basic level. But if I am notorious, I can again tweak, because I don't want that my son should die. So, again, I make my model viable, okay? But I'm just giving a picture that why we need precision. First of all, these are fundamental parameters. We never asked question, why should I measure the electron mass so precisely? Have you ever asked this question to a teacher? We just believe that, okay, electrons are there, we need to measure the mass because electron is everywhere. We need to know the properties of electron. I want to convince you that neutrino physics has reached that stage that we also need to know these 6 oscillation mass mixing parameters very precisely. No question asked. These are your fundamental parameters of your theory. You need to have more experiment, you need to measure them precisely, but the consequence will be very, very high, remarkable. When you start measuring precisely these mass mixing parameters, you will be very close to identify the right new standard model. Because in that process, you will be eliminating many, many models, because all these models have their different allowed ranges of the parameter, right? Once you know that I know 6 parameters and they're only allowed in this range, immediately you start ruling out many models. The vanilla version of those models, right? So, I'm not doing any calculation, but I'm just giving an idea. You can start playing that game. After this school, just see what are the data available, and you just go and pick up your favorite neutrino mass models and do this analysis. Still, it's a viable project. Nobody has done that. There are some activity around 2012 when θ13 was discovered. But in last 10 years, there are huge progress. So you can do that exercise again. Literally, you can do that project for your PhD. Start, that, okay, I have this X category of models, their predicted values were that, this is my data, so I rule out this theory at some confidence level. Now, how to treat this data theory, this analysis part, Adam is teaching you how to do this calculation, correct? Clear? So, the only way we can understand, we can get a bigger picture about the right neutrino or new standard model with neutrino mass mixing parameter is to over constrain those values. Okay, because I'll be talking about them. If I can't motivate you, why will you spend 3 hours listening to me? Right? So clear? We really need to measure these parameters, but the life is very tough. But we have some solutions, we have some way out. That will be the correspondence, that will be the dialogues for next 2-3 hours between me and you. Clear? Okay. So, non-zero neutrino mass, very important. First experimental proof for BSM physics. Now, this is also a very hot topic of research, effective field theory. There are many groups in India working on that. How to invoke in an effective manner these new phenomena in your theory. So in that effective field theory approach, you can write down the Lagrangian where you have the standard model part and then you have these higher order terms, right? Now, this first piece, this is the dimension 5 Weinberg operator. I strongly urge you, please open this paper for one time during this school. Please open this paper and classic paper by Weinberg and just go through it. Okay? Even if you don't understand, just read it, please. And in that paper, you can see how he expanded this effective Lagrangian, and this first term gives the neutrino mass, and here lambda is the new physics scale that you want to probe in an indirect manner in your low energy experiment. And this dimension 6 gives you new interactions. This gives rise to new neutrino interactions with ambient matter particles, which we call non-standard interactions. Some of you are familiar, right? So these BSM scenarios naturally arise when you want to invoke these parameters in your theory beyond the standard model scenarios. And once you want to do that, the outcome is interesting. You immediately land up with new particles, new interactions, new sources of CP violation, lepton number, lepton flavor violation, possibilities of exotic scenarios like low range CPT violation, decoherence that you wrote the paper today, all these non-standard interactions, decay. So now in neutrino oscillation, we are in the precision era, I told you. So neutrino oscillation is a very tiny phenomena. You can think of what is the value of the parameter delta m square by twice e. Just calculate in your mind. You have seen, okay, we are seeing for last 10 years, neutrino oscillation have been discovered. We have seen so many data and blah, blah, blah. But the phenomena is very tiny. Because you know the vacuum expression, what Andre taught you. What was that? Delta m square by twice e, u dagger, right? In the Hamiltonian, correct? So vacuum oscillation is driven by mass squared splitting over twice e. Or if you invert it, that is the oscillation length. Now just calculate delta m square by twice e, how tiny that number is. Just imagine, if you don't appreciate that, you can't appreciate oscillation. This quantity is very tiny, right? What is the value of this? Typically say 10 to the power minus 3 eV square or 10 to the power minus 5 eV square, correct? Now take E 1 GeV. Calculate this value. So this is what you probe in your experiment. But this is a very tiny number. And that is the triumph of neutrino oscillation, that we have been able to detect such small effect in our experiment. Correct? So now we have measured these parameters with sufficient precision. And these are subleading effects. So any small new physics can also show up there. Okay? Fight becomes interesting when Punjab King is also doing well, RCB is also doing well. Koi bad gaya to. So in both the teams are doing good, you see the match, right? So here, if your new physics is very tiny, but oscillation itself is very tiny, then when you want to do some analysis with two effects together, either they can interfere positively or negatively, right? They can affect each other. If someone is very big and dominant, then what the next guy will do? But if they are comparable, then they can affect each other, right? I'm just trying to give an idea. So when you expand your Hamiltonian, when neutrinos propagate in matter, if I have some new interactions because of this dimension 6 operator, and those interactions are also small, but the main piece in the Hamiltonian is also very small, so then they can interfere with each other, right? And then you can ask, okay, I'm measuring my oscillation phenomena very precisely. Do I have an opportunity to see these BSM effects, which are also very tiny? Make sense? So just whenever you think about any new physics, non-standard interaction, Lorentz violation, CPT violation, decoherence, what not, you just first think that how can I write another piece in my Hamiltonian, correct? Now, if that another piece, how that will look like governs by your new physics scenario. One of the example is new interactions. You know that MSW effect, right? And they talked about. When neutrinos passes through matter, there is Wolfenstein matter term. There is a matter effect happens. I will talk about that. But you can have additional interactions if there are some BSM physics is there. And that can arise because of this term, this dimension 6 operator, and we call them non-standard neutrino interactions. So what would happen? If you write those terms, they will change your oscillation probability. But what I'm trying to convince you, the moment you write down the term because of this new term in your Lagrangian, that term and in your zeroth term, which is your vacuum oscillation, they are comparable. So these things, I wrote very carefully here, they can leave some noticeable effect in your oscillation experiment. So if you ask me, the phenomenology of neutrino oscillation, this has become an industry now. And I can see here faces, many people are also involved in those studies. We are asking randomly, can I see this, can I see that? If I don't see that, I constrain them. Okay? So neutrino oscillation has taken that next step. Because other situations are kind of under control, so you can invoke some more parameters and see what they will cost to your experiment. You have the data. If you don't see any excess, Or if you don't see any departure, you say, okay, these terms are very small or zero. And you put bounds. Are you getting the idea of the phenomenology? I stop here for 10 seconds. Ask me if naively, because I'm not going to board, I'm not telling you ki padho ye karo, I'm just telling you the big picture. Is that clear? Why all this new physics all of a sudden has become so important to us? Two reasons. Oscillation itself a tiny phenomena. So if another tiny phenomenon is happening next to you, they can show up. And second, thanks to our experimental colleagues. They are detecting these neutrinos with infinite precision. Okay? Two things, period. And then, we are smart enough with our laptop to do our analysis. Correct? So, what I find, there are two areas where, most of the things are happening these days. One is, you probe these BSM physics at very higher energies. And the most important candidate is ice cube at the South Pole. Another candidate is, there is an experiment at the Mediterranean Sea. So people have not only gone to ice, they have gone to sea also. And this experiment called KM3net in Europe. And it has two experiments. One is ARCA, the bigger version. And the ORCA is the inner side of the detector, where you do the low energy physics. So these are big neutrino telescopes. And then I talked about ice cube Gen 2. So when you want to do phenomenology at higher energies, flux is very low, you need big neutrino telescopes. But I should say that these are neophysics beyond the reach of modern colliders. I told you, the energies that you probe, TeV, PeV, you will not be able to generate these energies in your lab. So you will not be able to test your theories beyond certain energies, but neutrinos give you that opportunity, right? If you want to, yeah. And then you have another possibility why neutrinos are exciting. Suppose you come up with a theory, you put bounds using high energy data. At the same time, I can tell you, okay, so then these parameters should exist at lower energies also. Then you have, at lower energies, you have these long baseline neutrinos, atmospheric neutrinos, these terrestrial experiments. Okay, correct? And there the baselines are few meters to thousands of kilometers. And there are many experiments that we'll be talking about. So these experiments like DUNE, Hyper-K or whatever, T2K, NOVA, you have heard about this name, I believe, from Andre's talk. They are expected to measure this oscillation parameter with a few % precision. And now if I tell you I have a new physics, which is also around few %, then they are of the same order, right? So they can interfere in your analysis and can show some signatures. If you don't see them, you put bounds. So I think this is very important. If you realize this, that neutrinos give you this opportunity, that the moment you come up with that, oh, okay, I have a candidate for new physics, immediately I am there to just put my hand on your throat. Because there are so many data at different energies, and you need to satisfy all the data, right? So you can test your theories in many ways. And that's why I say the phenomenology is very rich. Make sense? I will not be able to go in detail, but I'm just trying to give you the flavor, okay? So this is a very well-known slide. So we had a fantastic 20 years of neutrino oscillation physics. I just talked about some of these experiments, and we have seen neutrino oscillation from all of these experiments, but mostly you see, we are dealing with the first or second generation neutrinos or anti-neutrinos, correct? But they are traversing different distances, their energies are different, but all of them are showing that they like to oscillate, correct? So let us briefly take a look at three flavors, because this is the main topic of discussion. So again, I want to pause. You are motivated so that I proceed. You think like, there are some interesting things, let's see. So if you are not, then you can sleep. Otherwise, listen carefully. But it is very important, that if you are not motivated, there is no point of sitting here. Okay, you need to, these activities are just to invoke the motivation, the excitement. Yeah, let's do something. I can do also some small calculation and see what's happening, okay? And we are just here to provoke you. So, 3-flavor neutrino oscillation. Why neutrino oscillates? Because when neutrinos are produced or detected, they are in their flavor eigenstate. They are at weak eigenstate. But when neutrinos propagate freely in space, they are in their mass basis. And for neutrinos, this flavor eigenstate and mass eigenstate, they do not coincide. I have a question. What happens for charged leptons? Very interesting question I always ask. So there another question. Do charged leptons oscillate? So think about that. And if you have any suggestion, let me know. But please write it down. Think about this. Do charged leptons oscillate? Why only neutral leptons should oscillate? Is there a finite probability? Believe me, I was asked this question when I gave interview 2 years back. So I'm not joking with you guys. It is important question. Same question was asked by me to me by a director of IIT. He asked me this question. So it's a relevant question. Okay? So think about it. So fine, we have this Ponte-Corvo, Maki, Nakagawa, Sakata 3x3 unitary matrix which tells us how you can connect the flavor eigenstate with the mass eigenstate. This has been introduced to you in 2-flavor picture. I have heard about this from Andre, right? What I will do, I will go to 3-flavor. So in this picture, this matrix is nothing but you have 3 rotations, Euler rotations, correct? All of you are familiar with rotational dynamics in your BSc courses. So you have first rotation around 1, 2, then 1, 3, and then 2, 3. And if you just put them in this order, this is the parameterization which we consider while we analyze our oscillation data. And then you get your PMNS matrix, right? Now, here on the extreme left, I have 1, 2 rotation, and in the extreme left, we have the 2, 3 rotation. And in the extreme right, 1, 2 rotation. Who told you or who told me that I should give the rotation in this order? Think about it. We are just habituated. We are taught like that. But you can switch the order. You can put this here, this here, this here. Your physics should be independent of basis, right? So now I have a homework, simple homework, if you kindly do that. Just calculate a probability of alpha type neutrino goes to beta, say nu mu to nu e or nu e to nu mu. And now you are doing computational also with Sushant, with globes. So you can do it analytically also. In vacuum, if you write down a probability expression, nu alpha goes to nu beta with this parameterization, and now you calculate the UP meanness by changing the order. And calculate the probability again. And see what happens to this theta 1, 2, theta 2, 3. Because there are 3 mixing angles, 1 CP phase, right? And you will see, some questions will arise there. These mixing angles are fundamental parameters, right? So how much is theta 1 to the value of theta 1 to? When we say 30 degree, 34 degree, we say based on this parameterization. But if you change the ordering of this rotation, then the meaning of theta 1 2, theta 2 3, theta 1 3 may change, right? But what is fixed in nature, try to think about what we measure in neutrino oscillation. Think about this mass eigenstate, this nu3 mass eigenstate. What we measure in experiment, how much is the flavor content is there in each mass eigenstate. U mu3, if you, okay, let me just quickly go there. This is your U mu3, right? This is that UPMNS matrix. If I multiply this 3 rotation matrix, then you get it, right? You are familiar with this? You can do it yourself. But what I'm asking you, you will get a different matrix if you change the rotation, correct? This 1, 2, 1, 3 will change their locations. So then this U mu3 and U tau 3 will look different, correct? Now what this U mu3 tells you, this component, this tells you how much muon flavor is there in the nu3 mass eigenstate. This tells you, this u tau 3, how much tau flavor is there in the nu3 mass eigenstate. And no matter what you do, these are fixed quantities in nature. Right? This is the oscillation probability. Oscillation happens because of this mixing, and that is fixed in nature. Now, how you parameterize them in terms of three name, I can say theta x, theta y, theta z, who cares? I may not work with this parameterization. I can go to another, say Wolfenstein parameterization. Fine. But physics will not change, right? So think about it. These are very basics, but just think about it. So when we talk about these three mixing angles and one CP phase, which is the content of this UPMNS matrix, what we measure is the ratio of these quantities, correct? Just think about this, because I will talk about a lot about theta 2, 3. U mu 3 square by u tau 3 square. Just write it down on your notebook. U mu 3 square over u tau 3 square. So you see, this is your u mu 3. This is your u tau 3. Take the square and divide. What do you get? Tan square theta 2, 3, right? So theta 2, 3 is just nothing but the ratio of how much muon content you have in nu3 mass eigenstate over how much tau flavor you have in the nu3 mass eigenstate. If somebody asks you what is the physical meaning of theta 2, 3, this is the physical meaning. Correct. So I hope you understand this. Another game you can play. You can ask me, why did you put delta CP over there? So you can also do this exercise. You can put this delta anywhere, right? You just need three real parameters, one complex parameters to parameterize a 3x3 unitary matrix, right? Also, this counting is very important. You are listening very big things. Go home and see whether you can estimate how many free parameters you need to parameterize a n cross n unitary matrix. Please do this exercise. Okay, at least you should learn this much, okay, from these lectures, because if you don't appreciate that, then there is nothing. So do this, very easy, parameter counting. So you can put this phase anywhere. So why don't you try? You try this, putting this phase with this angle or this angle, and you write down again nu mu to nu oscillation probability and see what difference you see. Please do that. Interesting exercise. Because you want to measure the delta CP phase in long baseline experiments, right? Many people, you are all working on that. So how will there be any change in the interpretation of delta CP if I put this delta CP here or here? Please, is a homework problem. Do that, very simple. So you all know this is the probability expression. What is the probability? Alpha type neutrino will oscillate to beta type neutrino. And you have, this is the real part where you have these various mixing angles. And this is the imaginary part where the CP phase comes into the picture. So in the oscillation probability, you have two pieces. One is the real part, one is the imaginary part. If delta CP is 0, then this part goes away. Correct? You have only the real part. So when you think about anti-neutrinos, the only change becomes U star, right? That means delta CP goes to minus delta CP. I am just giving you the basic pieces so that you can connect when you go home. And in that three flavor scenario, you have these three mass eigenstates. So you have two independent splittings, correct? M1, M2, M3. So how many independent splittings? Only two. M1, M2, M2, M3, or M1, M3, M1, M2, right? You have two independent splittings. So this is the game of oscillation. 4 parameters from your UPMNS and 2 independent mass splitting. Correct? So I gave you some homework problem. Those are very interesting. Do that. So I will stop in 5-10 minutes. So this is the picture in another way. You have these 3 rotations. By the way, I want to mention here, you didn't ask me this question, by the way. Why we prefer to go with this parameterization? So this mixing angle, theta 2, 3, which I will discuss a lot, is mostly measured by long baseline experiment and atmospheric neutrino experiment. That is the topic of these lectures. Tomorrow you will see. In the extreme right, when I talk about theta 1, 2, this mixing angle is mostly measured by the solar and reactor experiments. Please remember that, okay? So this theta 1, 3, which was the last mixing angle that got discovered in 2012, this is theta 1, 3. And it was discovered in reactor anti-neutrino experiment. And at the same time, experiments like T2K NOVA also found a non-zero value of theta 1, 3. And now in atmospheric neutrino experiments also, we are seeing that this theta 1, 3 is non-zero. Okay, many things are happening. But I want to stop today by telling you that when you want to measure this parameter, you are working in the atmospheric sector. Because if you don't make things clear now, my future lectures will be just, you will be listening and you will be forgetting immediately. There will be exponential decay of whatever I'm telling. But if you appreciate now, you will be able to remember. When you want to measure this extreme left rotation, you are working at atmospheric frequency, and this is the kind of the best fit value we have for the splitting between M2 and M3. Now to probe this, you know the oscillatory term that Andre has written. What was the term? Can anybody tell you the oscillatory term? Be loud, just tell me. What was the oscillatory term when he wrote two-flavor oscillation formula? जोर से बोलो ना, मैं भी तो बोल रहा हूं. Delta M square L by 4E, right? So there was a L by E term over there with a product with delta M square. So if you want to make that argument of sign reasonable, like finite, so then this L by E or E by L has to be of the order of this delta M square, right? So this L by E that you probe is around 500 kilometer over G. Now, solar mass splitting, which is the difference between M2 and M1, which is almost 30 times smaller than the atmospheric splitting, right? Can you see these two values? If you take the ratio of this quantity over this quantity, it is roughly 1 by 30. Correct? This is 30 times bigger than this. No, you can just calculate. So then to probe this quantity, you need 30 times more L by E values, right? This is 15,000. And indeed, you know, this kind of L by E you need to probe this mixing angle, and this kind of L by E you need to probe this mixing angle. Make it very clear. If you have any doubts, you can ask me during the breaks or tomorrow, anytime, because this is very simple thing. Okay? Even anybody, you know, can appreciate that. You don't need me to appreciate this also. So initially, when we started seeing the neutrino oscillation phenomena in various experiments, you had the solar neutrino anomaly, right? And then once we solved the solar neutrino anomaly, then we had these reactor experiments also come land to see whether that thing happens in a lab experiment or not. So that time, we were okay to analyze the whole data in a two-flavor framework. There was no need of these two rotations. 15 years back, when you want to fit the solar and reactor anti-neutrino data, it was sufficient to just take one rotation, this much. So you are in a two-flavor regime, and you had a very nice fit. Correct? At the same time, atmospheric neutrino anomaly came. There, people were happy to just take two flavor, nu mu and nu tau. For the solar, it is nu e and nu mu, because your starting point is nu e, right? So they thought, okay, in a two flavor scenario, I can fit all the solar and reactor data, and you get a sufficient good fit, and you could measure theta 1, 2 and this delta M square 2, 1. You are happy. This is two flavor picture. At the same time, in Japan, neutrino oscillation was discovered in atmospheric neutrino experiment. The L by E was 30 times smaller. To explain that data, that 50% of nu mu is oscillating to nu tau, only this one rotation was sufficient enough. You just take U to be two flavor matrix, 2 cross 2 matrix, and you can get sufficiently precise values of delta M square and theta 2, 3. Correct? There was a twist in 2012. The moment, so initially, people thought, okay, we are okay with this two flavor picture. The moment we discovered that this theta 1,3, which was thought to be very small or almost zero, that it is non-zero in 2012 by Diabe with more than 5 sigma confidence level, I think that is one of the turning points in the history of neutrino oscillation physics. In my opinion, that was remarkable. The moment we got to know that this theta 1,3 is non-zero, our life expanded. We all got to know that two flavor is an approximate picture. We need to analyze all the data in a full three flavor picture. And whatever you have measured, assuming two flavor, they will get some correction due to finite theta 1,3. Because theta 1,3 is not zero, it is 8 degree, 9 degree. So it will give you some tension and some correction in your earlier knowledge, right? As well as you have to measure theta 1,3. And this theta 1,3 we are probing in modern reactor experiments and long baseline experiments like T2K, NOVA, and also in atmospheric experiment now. So I must say that was the turning point in oscillation physics. We were convinced that we are in three flavor. We have to reanalyze all the data. And at the same time, see why delta Cp was put against theta 1,3. In two flavor, there is no scope of complex phase, right? You need one real parameter. So people thought, okay, do not invoke delta Cp. I am fine with theta 1,2, I am fine with theta 2,3. The moment theta 1,3 got discovered, you have an opportunity that let's put in delta Cp. With who? With theta 1,3, because that was the last unknown mixing angle. The moment theta 1,3 is non-zero, you are in three flavor, you have a scope to invoke delta. So there is some history is involved. That's why delta is always put next to that, and also we follow the CKM parameterization. Make sense? So the moment theta 1,3 is zero, if S13 is zero, even if there is a Cp violation in nature, you can't invoke them in your oscillation. So oscillation will not be able to tell you whether Cp symmetry is violated in neutrino sector or not through oscillation. They may be violated, but you don't have scope to invoke delta in your picture. So very clear now why delta was put here, all these things. Okay, so I think this is the right time to stop. So we will proceed from here. But again, I went very slowly today to set the stage, and some of you might found everything, I know everything, and that's fine. But I asked some questions, go back and try to think, because there are many twists are there, whatever I just told you. But if you appreciate this, then you will appreciate next two lectures. Okay, and if you have any questions, if you see me, we can discuss among yourselves, or maybe you can discuss tomorrow.
We can take a few questions.
Yeah, you can. If you have questions, you can take now. Yes. Bolo Tej.
We are measuring this parameter.
Yes. Do neutrino astronomy. How are these going to help us? Both of these are quite independent, right? Okay. So there are two things. Neutrino astronomy means low energy neutrino astronomy or high energy? Oh, so you are working in Ice Cube, right? Ashish. Yeah. Oh, Ashish. You did a project with me. Okay, now I remember. So Ashish, in high energy astronomy, the thrust is to discover the sources. Okay. Now, when you discover these sources, when you have more events in your Ice Cube or other experiments, your oscillation doesn't come into the picture because the coherence is lot. Because what is this oscillation? The idea is there is a coherent superposition of mass eigenstates to form the flavor eigenstate, right? But for solar or supernova neutrinos, because there is some mass difference, and if they have some velocity, after certain time, the wave packets will be separated, right? And if you allow more time to travel, when they reach at your Earth, the wave packets are already separated. There is no coherence anymore. So when you have megaparsec, gigaparsec distance, these cosmic distances, to see these ultra high energy neutrinos, there is no oscillation, but there is a mixing. So you must have seen the ternary diagrams, the flavor ratio diagrams. Have you seen for ultra high energy neutrinos? Have you seen these diagrams by IceCube where you have like, these are the ternary diagrams in nu e, nu mu, nu tau. So typical understanding is when high energy neutrinos are produced in AGN, GRBs or anywhere, those are mostly pion decays, right? So the ratio of nu e is to nu mu is to nu tau is 1:2:0. This is at source, correct? Now, when these neutrinos travel astronomical distances to reach at South Pole, already the wave packets are separated, correct? You understand? Coherence is lost. So interference is not there. But you can't prevent the mixing. So if you just take this ratio at your source and you wanna measure the ratio, so since you asked Ashish and you are making me to work, you should also work. So you calculate this and show me. This is at Earth. Calculate this. Take the UPMNS. You know the UPMNS matrix. And your source was 1:2:0. Correct? You can do that. You just need to calculate these elements, right? So this is the probability between E to E, E to mu, E to tau. So here it will be like PE, PE mu, PE tau, P mu E, P mu mu, P mu tau, P tau E, P tau mu, P tau tau. Make sense? P is what? This is nu E to nu E probability, right? You can calculate. These are all just, there is no oscillation frequency. It is mod U square times mod U square, right? Only mixing. Okay? If you assume in your 3 flavor formula that delta M square has been averaged out because the separation is large, you have only mixing. So then when you estimate your flavors at the Earth, your mixing is coming into the picture, right? So did I answer your question? In high energy neutrino astronomy also, this is the standard picture. That standard picture tells us the flavor ratio at the source is 1:2:0. Now, if you agree with me and go with the standard oscillation parameter, you can check this ratio will become 1:1:1. You should do that and show me. Very close to 1:1:1. Now, with IceCube, we have started measuring all the flavors, nu E, nu mu, nu tau. There was a PRL paper. Recently, IceCube has seen 7 astrophysical tau neutrino events. And that is the triumph in this business. We have started probing the tau flavor also. So now we are measuring this ratio at the Earth. But to estimate this ratio, this U comes into the picture, right? So that's why if you over-constrain this parameter at your terrestrial experiments, those are going to be super helpful to predict the high energy astronomical fluxes at the Earth. Did I answer your question?
Sir, can you throw some light on the assertion you have given that why do we need to put the CP phase with the 1,3 matrices?
Very good question. So why do we need to put, so your question is why can't we put it here or here? This is the question, or why at all delta CP I should put? What is your question?
Why it comes with S1?
Okay, so I told you, initially we thought that this θ13 is almost 0 because till 2012, from reactor experiment like Shaw, Palo, we had an upper bound that θ13 should not be more than 10-12 degrees. So then any value was allowed below that, even 0. So most of the time, to do an economical calculation, we were taking it 0, and we were happy to fit the solar and the Kamlan data to measure theta 1, 2 and delta m square 2, 1. Because it is two flavors, so you don't have a scope to invoke delta CP. And we were happy. At the same time, in Japan, Super Kamiokande saw the atmospheric neutrino anomaly, the oscillation of nu mu going to nu tau. So in their initial phases, they analyzed the entire data in a two flavor picture, and you again don't need a delta CP there, correct? So we just went with the history, and we had these two rotations, and then we kept the unknown parameters for future with the remaining unknown, because theta 1, 3 is unknown. If I make it 0, delta CP is also gone. I don't need to care about them, and I do my two flavor fit. I'm happy. The moment theta 1, 3 got discovered, then we had the opportunity, because we are in three flavor, and you are now allowed to invoke the delta CP. So why to make this situation complicated putting deltas there? You put the delta there, and this is also the CKM parameter. In CKM sector also we follow that, so that we can have a direct analogy. But this is the homework I gave you. If you are not happy with me, fine. Then you put delta CP there, delta CP here, one at a time, and calculate nu mu to nu e oscillation probability again, and see how the interpretation of delta changes. This is a homework problem for you. Make sense? Yes.
Sir, I have a follow-up question regarding this. So before, when the solar and reactor data were analyzed and the atmospheric neutrinos were analyzed, so in atmosphere we know we can't know the polarize, like if it is neutrino or anti-neutrino during that time, right? If it is neutrino oscillating to neutrinos or anti-neutrino oscillation.
Because you can't separate them in Super Kamiokande.
Yeah. But I'm saying we know the solar neutrino, the solar are the nu E flavor, and they are a reactor anti-neutrinos, right?
Nu E bar, yes.
Yeah.
Correct.
So if there was possible CP, like it is already three flavor picture, but that was confirmed with theta 1, 3 non-zero.
Correct.
But let's say like it is CP violating in nature.
Correct.
But then theta 1, 2 in solar and reactor sector, they are same flavor, both pure flavors.
Right.
So there it should have been seen even from the two flavor picture, right?
Very good question.
And
so,
then if it is not seen, that means it should not reside with theta 1 through.
So, very good question. Let me answer step by step. I'm glad that you are going there. So, when you are in two flavor, this is an approximation. So, you are fitting your solar and Kamlan data with two flavor, and you know that I am not taking care of theta 1, 3 and associated delta. And now, if you fit the data in two flavor, and if you see the mismatch, then that mismatch may be due to because you have approximated the thing. And because of the approximation, delta CP is also not coming into the picture. But even if in three flavor, if you write this formula, in solar, what you probe? The survival of nu E to nu E, correct? In solar experiment, agree? And in Kamland, it is a reactor anti-neutrino experiment. So you probe this channel, correct? Agree with me? Even if you take three flavor and just do this is also homework for you. Take the vacuum, this formula, and take alpha is E, beta is E, and no matter effect. Just write down this formula. You see whether delta CP appears in the expression or not. I am writing no delta CP.
Yeah, in the vacuum it doesn't appear, but I'm saying in case of...
You write it in matter also? Okay. You write it in matter and see whether delta CP appears or not. That's why, whether you are in matter or in vacuum, the nu E to nu E survival challenge. In fact, we wrote a paper, when I was a student, she came to my office, hey, why don't you work on that? So nu E to nu E and nu E bar to nu E bar. No matter what, you are in vacuum or matter, you are free from theta 2, 3 and delta CP. So that's why those channels gives you very clean measurement of the major angle, whether it is 1, 2 or 1, 3 and the associated frequency. Don't rely on it. Please do this calculation. Theta 2, 3 and delta CP will not appear until unless you really deform with some new physics and all. But theta 2, 3 and delta CP will not appear because it is U Eij square U. So because this probability is nothing but Ui mod square Okay, so it is e to the power minus I delta, so it will vanish, e to the power minus I delta plus I delta. So delta will never appear, and also theta 2, 3. Please do that. If you have problem, discuss with me. So even if in 3 flavor, those 2 experiments will be always remain blind to delta Cp and theta 2, 3.
Discussion, but I also want to, I want to agree with Sanjeev said, you can put the phase in 1, 2, and 2, 3, and please see what happens.
Please see what
That's really a good.
Yeah, because you can write a small note, even archive, you can put it. No, if you start doing, we can tell you many things. Just do this calculation.